Okay, here's a replay of today's lecture where we talked about assigning oxidation numbers. We're going to worry about this portion here a little bit later when we get into class tomorrow. So um, this middle section here is really set up for our rules, okay? And there's three main ones here that we're going to focus on most of the time. Actually, this one as well. And that is that the elements that are uncombined have a oxidation state of 0, which means they haven't gained or lost any electrons. The second one is hydrogen generally gets a +1 charge, except for in the case of hydrides, which we'll address later when we come into contact with those. And then oxygen is generally a -2. These two numbers here are really going to drive a lot of things with us identifying where we have changes in oxidation states, because these two don't change at all, except for in the case of peroxide, and that will be very apparent. It'll show up something like this, where each one of these oxygen has a negative charge of 1. Because I have two of them, the overall charge for both of them becomes -2, where hydrogen is +1 because we have two overall charges too. It's important that we differentiate between the charge of the individual atom and the charge of the atoms that are bonded to the other components of the compound. All right. So while each oxygen has a -1 charge, all of the oxygens here together work together to create a -2 charge, and we have to have enough positive charges to balance it out. Remember that when a charge is negative, that just indicates that electrons have been pulled or are given to that element. So I can't have more electrons being gained than are being given off by the hydrogen. Okay, so that's why we're always going to have a balance here between our charges. Okay. Some other things: elements other than oxygen and hydrogen in a neutral compound is such the sum of the oxidation numbers for all atoms is to be 0. We'll see that a bunch of times in here where we'll have the oxygen and hydrogen have a charge, but then what do we have? What is the third thing? And we're just trying to make a neutral one. And likewise here, if we have to match up to what a charge is for compound. So what does all that mean? That's a lot of talky talk, but I just want to make sure that we have that as a reference. What does that mean for oxidation number? Well, oxidation number is basically the charge that something has when it's either bonded or in solution. So barium, first of all, it's actually an ion in solution, and typically this could also be a gas, but we usually don't deal with gases in our lab. But barium here actually tells us the charge, so the oxidation state or oxidation number for it is +2. Nitrogen, this is going to follow our monoatomic, our uncombined element rule. So because it's only bonded with itself, it's going to have a charge of 0. The next one here, we have H and I. Hydrogen is a +1. Okay, it follows our hydrogen. This is not a hydride. Therefore, hydrogen is +1. Okay, we're used to seeing this one. This one over here, this is peroxide. And this one does tell us the charge is -2 because we have two oxygens. Each one of these oxygen is going to have a -1 charge. Whenever we list the oxidation number, we are only listing the charge for a single element, okay, not the pair as a whole. Okay, we're going to list for one element. All right, let's look at the next one here. We've got silver and bromine. All right, for these, having a chart where we have our where our ions are listed are helpful. Okay, in this case we have Ag, silver, which is positive, and Br, which is over here as a halogen, which is -1. Okay. With this one, the metal, or I'm sorry, the non-metal here, bromine, is really going to help us indicate it because bromine very rarely comes off of this -1 charge. Most of the things that we're going to see have variable charges are going to lie somewhere here in the middle, okay, or in this lower part of the non-metals up here, okay, phosphorus, sulfur, selenide, silicon. We see them change their oxidation numbers quite often, including carbon, okay. So we're going to go with standard charges on things when possible. Typically where we see oxidation numbers change is when we are going from something like this and breaking it apart. Okay, so HNO3. So let's look at copper chloride. Chlorine typically has a charge of negative. It is one of those halogens here in the family 17, okay, Cl minus. Because I have two of these chlorines, the overall charge for the chlorine side is -2, making the copper charge +2. Okay, let's look at HNO3. Hydrogen, this is +1. My oxygen is -2. We have 3 oxygens here, so the whole charge for all of this, okay, all 3 of those collectively is going to be a -6. All right, so if this is -6 and this is +1, our whole compound as a whole isn't displaying a charge. This nitrogen here is going to be +5. We see this a lot where the element in the middle, okay, is going to be the one that has a non-standard or non-typical charge. Nitrogen, when we look at our periodic table of ions, we see it having a -3 charge a lot. However, because it's attached to an oxygen, that oxygen has a very strong pull towards the electrons, which allows it to pull some of the electrons towards it. ClO3 minus. All right, so oxygen is -2. I have 3 of them, giving me a -6 charge for everything all together. Now, this all here, I'm going to move this negative out here so I can see things a little bit better. All right, so if I need this whole compound to be negative, and I already have -6 on the oxygen side, that's going to mean my chlorine here will be +5. Okay? And we see that happen a lot with these nonmetals because oxygen is so strong. Oxygen and fluorine, they can overpower another nonmetal and kind of pull its electrons towards it. So it's not an unusual occurrence to see. Let's look at SO3. We're looking for the sulfur. So oxygen is -2. I have 3 of them. So my total negative for the oxygen side is -6. So the oxidation number for oxygen is -2. Sulfur is +6. It's +6 because our negative charges and our positive charges need to balance out to be 0. Let's look at the next one here. I've got SO3, and this is -2 or -6. Okay, and then Na is a metal, which we typically see having a charge of +1. I have 2 of those, so that is +2. And so when I look at the sulfur here, the sulfur is going to need to be a +4 as well. Okay, actually, yes, it would be +4. Okay, in order to balance it out, I've got +2, -6, +4. So the 2 and the 4 balance out the -6 value for the oxygen. So the oxidation number for sulfur is going to be 4. Let's look at this one. Okay, so oxygen is -2, our standard. Okay, barium is a metal. Our metals are going to stay pretty much the same unless they're monoatomic. And so I've got -2 for the oxygen. I do have 4 of them, which puts this at -8. Okay, and so I've got a -8. This is a neutral element altogether. So -8, +2. This chromium here is going to be +6. Okay, so when we're determining the charge of an individual atom, okay, we have to look at the charge of all of the other atoms, okay, together and see where it fits in. Let's look at CaSO4. Typical charge for oxygen is -2, -8 because we have 4 of them. Calcium is an alkaline earth metal, okay, which is +2. All alkaline earth metals, okay, fall in this column right here. versus the alkali metals. These tend to not change their charges. Okay, so we can depend on them. And what's in here? -8, +2, and I need this to be neutral, so this will be +6 for the sulfur. Okay, so we are just adjusting our value. Specifically, we find it in this first element of a polyatomic ion, and it's because it can get affected by the pull of the electrons from the typically the oxygen on the right side. So those are our oxidation states.